Good morning to all. I am happy to say few words about our college and the department. Our Francis Xavier Engineering College is popularly known as FX Engineering College. It was established in the year 2000. Our college has obtained many awards. We got gold category for Industry Linked Technical Institute awarded by AICTE CAI survey. In Chronicle Engineering College survey, we got third among 19 engineering colleges in India. Chronicle South Zone B School, our Francis Xavier Engineering College, obtained 15th rank in that survey. In Times Best Engineering Colleges survey, our college has obtained 15th in Tamil Nadu and 108th in India. In Outlook Top Engineering Colleges survey, we got 141st place in India. Digital Learning Magazine is a Asia premier magazine for ICT education. It awarded 4A status for our college. The Global Human Resource Development Center Engineering College Survey has awarded 13th place in Tamil Nadu. Apart from that, we got ICT Academy Tamil Nadu Academic Partner Excellence Award in the year 2017. Then regarding our department, we have FANUC Center of Excellence for CNC training and BMW and Hyundai supported automobile lab. Our department has signed many MOU with leading manufacturing, service industry, process industry and training centers. We offer international certification program in CAD and NDT. Our students are actively participating in many technical competitions, winning prizes and bring laurels to our department. The research areas of our faculty members are bioenergy, combustion, solar desalination, green manufacturing, composite materials, waste heat recovery and biomass gasification. We have organized many international conferences, workshops and funded seminars. I hope this session will be more useful for all of us. Thank you.
Good morning. It gives me immense pleasure in introducing the chief guest of the section. Dr. I.A. Palani is an associate professor and the Dean Research and Development, IIT Indo. He completed his PhD from IIT Madras in the field of laser-assisted semiconductor processing. During his PhD, he received Haichu University Fellowship from Japan to pursue his research for the period of 1 year. Later, after his PhD, he got an offer from Haichu University to work as research scientist from 2010 to 2012. He joined IIT Indo in the year 2012. He was the founding head of the discipline of metallurgy engineering and material science. His area of research includes mechatronic system design, shape memory alloys, laser assisted micro manufacturing and surface processing. He has published more than 100 international journals and 150 conference publication and 8 book chapters. He has filed 6 patents in the field of shape memory alloys. He was nominated as the president of SPIA student chapter in the year 2017. He is the recipient of Research and Innovation Alumni Award for the year 2015. He has guided 9 PhD and 15 ME students till date. He has been implementing projects from DRDO, ISRO, DST, SERB, DAD, Russian Science Foundation, JSPS and Royal Academy of Engineering UK worth rupees 8 crore. He has strong collaboration with industries such as Volvo, Easter, Job, Derby, Wapco, etc. He was invited as visiting professor in the Petersburg University, Russia, IFW, Dresden, Germany, Haichu University, Japan, Cambridge University, UK and Camfield University, UK. Thank you. Good.
So, good morning to one and all present here. Thank you very much for giving me this opportunity to present my work over here. So, slides there is Ingla? Okay. The topic which I am going to discuss today is something related to development of shape memory alloy for advanced manufacturing and robotic applications. So, basically, under this, before going into this topic, let me just give you a brief overview about my institute. So this institute is almost 10 years old institute, and I have been working in this institute for the past 8 years. So this has been ranked well. In fact, in the current NIRF ranking also, it is on the 10th position. So this is about my research group. So I come from mechatronics and instrumentation. So this is my overall research group. So we have a strong postdoc and PhD students. So basically, we focus towards this automation and control, lasers and optomechatronic system design, smart materials for micro devices, etc. Okay, so before going into this, so let us have a brief overview about this one. So as far as this biomimicking is concerned, we all know actuators. When we hear the term actuator is nothing but, so when you try to give an input signal, so you get an output in the form of displacement. So that is what is called as an actuator. So as far as actuators are concerned, like for most of the conventional actuators which we use motor as an actuator, but that is not possible for many kind of applications, such as in the case of biomimicking, such kind of biomimicking applications, it is very difficult to follow such kind of actuation. So in those conditions, it's better that we use an actuator, so which mimics the biomimicking capability in nature. Okay, so shape memory alloy is one such actuator which has a biomimicking capability. Let me just give you a small video on how a shape memory alloy works and how it basically biomimics the capability. So here I'm just going to show you a small video. So where you can just see a shape memory alloy is being used. Yeah, it has been programmed in the form of a lotus leaf. So this is a lotus leaf. This lotus leaf is made of metallic petals. When I try to heat it, it enlarges. When I try to cut off, it comes back. So here we are trying to mimic the biomimicking capability of a lotus flower, just like that. Okay, so this is an added point with respect to the lotus behavior. Okay, so as far as in this term is concerned, okay, so as far as in this term is concerned, let me just go back to the slides. So this is the overall family of the shape memory alloy. So as far as in this family is concerned, if you see, so there are wide variety of smart materials which are available. So among this, shape memory alloy plays a major role. So as far as in this shape memory alloy is concerned, it is basically designed based on the actuation stress and the actuation strain. So if I try to closely observe it, this shape memory alloy has been first developed in the year 1938 by Orladov, okay, where it was observed that the nickel titanium based ordnance laboratory has taken up a major role in it, and based on this nickel titanium naval ordnance lab we have worked on. So this naval ordnance lab basically has looked into the characteristics of the shape memory alloy. So as far as the shape memory alloy working is concerned, it is similar to your phase transformations. You have a solid and liquid and you have a gaseous phase. From solid it is getting transformed to a liquid, and from liquid it is being transformed to a gaseous phase is concerned. So we have a solid phase which is being kept and which is being transformed. So this is how it works. So basically in this work we have a austenite phase, we have a martensite phase, and we have a tweet in martensite. So So in this aspect, so when we try to look into it, so we have an austenite phase which is being working out. So this will give you a better clarity. Like initially, this is on a martensite phase. Now I am deforming this martensite phase. So this is on a deformed martensite. When I heat it, it comes back to the austenite phase. Then again, slowly it comes back to the martensite. So by that, when I try to give the hot actuation, so it tries to expand it and it comes back. So this is the overall perspective of this shape memory alloy based actuation characteristics. Okay, so now we have to look into some of the behavior where we are exhibiting some of the characteristics where I have a shape memory alloy which is being embedded into it. By trying to actuating it or just placing it in hot water, so it comes back to the original shape. So this is the overall combinations where the shape memory alloy is being embedded. One is nickel titanium base, NiTA base, CuZn base, CuAl base, and Fe based shape memory alloys are some of the shape memory alloy based combinations which exhibits shape memory behavior. So these are some of the applications with respect to the TDS training. So as far as in this training is concerned, there is going to be a repeated cycle. With respect to the cycle, you will be moving upon. So the overall challenges which are involved in it is one is a TDS trading, another one is influence of composition, third is the thermomechanical behavior, fourth is developing towards the required shape memory alloy aspects. So as far as in this case is concerned, so these are some of the basic challenges which we are going to look into. Okay, so first let us talk about some of the aspects of developing a commercial structures. So this is the overall content of my talk, where we will be talking about one of the characteristics called shape memory alloy bimorph. Okay, so as far as in this shape memory alloy bimorph is concerned, so there are, so we have developed some kind of bimorph based structures, which I would like to explain it over here. So as far as this bimorph is concerned, let us consider I have a thin film. This thin film is coated on a bimorph. So one way of actuation is happening because of shape memory alloy, and the return way of actuation is happening because of the bimorph. So like that, we may need to work on it. So as far as in this case is concerned, so the major chunk which what we are getting it over here is basically like this bimorph has a potential application in such a way that so to get a one-way actuation, so we are just trying to coat this layer something like this. So this is a layer of polyimide bimorph. Over this polyimide bimorph, I have a deposition. I have deposited it, so I am just giving a strain to it. After a deposition, you are just trying to go on heating, and when I try to heat it, you get a thin layer which is being fall down. So using this thin layer, then when you try to actuate it, so you get such kind of arrangement where there will be an opening and closing of the system. Unfortunately, this is not working. So where it is something like one way of actuation happens because of the movement, and the other way happens because of the return stroke. So with this, we can have a potential application towards such kind of dragonfly kind of arrangement. So that in this dragonfly kind of arrangement, by continuously actuating it, we get a movement in such a way that you can go for a lift kind of structures. Okay, so we went for a detailed analysis in this. So one detailed analysis what we have done is basically, so we have looked into the different structural and electrical characteristics of the system. So we went for different what you call substrate behavior, and when we tried to explore some of the substrate behavior, so we went on to a detailed analysis. This is one setup which we have developed in our lab. So in this setup, what we have done is we have used a bimorph, and we have coupled with the programmed power supply. And this is a laser displacement sensor. And in this laser displacement sensor, there is a kind of this laser displacement sensor is acting in such a way that the light will fall on this layer, and there will be an opening and closing of the system. So with that, you can measure how its behavior through. So this is copper-based shape memory alloy bimorph, where you have a heating and a cooling cycle. So in this heating and this cooling cycle, where there is a displacement and a temperature. So with respect to the displacement and the temperature, you can observe here you can observe the heating and the cooling characteristics of the system. By studying the heating and the cooling characteristics of the system, we can study the in-depth activities of it. So here, so this is the heating and the cooling cycle which is being observed, and this is the displacement and the number of cycles where we have come up in a single plane. Okay, And this is how a contact is being established. In this contact, so you have a CuNi based polyamide bimorph, and by opening and closing of this contact, you can have a influence in the system. So basically, by changing its characteristics, you can have an influence towards the varying thickness, as well as you have an influence towards the growth substrate temperature. Okay. Now we have a DSC characteristic which is there in place. So with this DSC characteristics, we can analyze what is the transformation temperature which we have developed in the thing. So basically here in this case, so what I'm doing is I'm just trying to fuse the material, and I'm just heating the material in such a way that this heated material is getting deposited, and then you can study the actuation behavior of it. So this is the overall characteristics of the actuation behavior, what we have observed, where we have included the influence of growth substrate temperature at DSC analysis, and where we have room temperature and we have a closed circuit. So with this closed circuit, we can observe what is happening. Okay, so this is the influence of Mn addition. Basically, we want to go for a improvement in ductility of this material. So what we have done is, so we have just incorporated an Mn into it. So with this Mn addition, we could observe that we can improve the life cycle behavior of it throughout the system. Okay, so this is the overall arrangement what we have made in our lab. So what we have done is, so we have made a copper-based shape memory alloy bimorph in the form of a wing. So when we try to actuate the wing, we can have a control over the frequency, and with this frequency, we can achieve a similar way, similar to a mobile robotic applications. So that is one good example. Let me just show you a video how we have employed the shape memory alloy bimorph with different combinations and with at controlled frequency. So this is with 1 Hertz frequency. So here you can see a kind of arrangement over here. This is your shape memory alloy bimorph, which is being embedded along the structures. And you can see a movement over here. So we can achieve any kind of movement. Basically, we have a constraint from 1 Hertz to 30 Hertz frequency. So this 1 Hertz to 30 Hertz frequency has been achieved using this system. So by using this, we can, so this is completely indigenously developed in our lab, and you can achieve a required frequency based on your own applications. Okay. Now we will go back to the slide. So now we are going to talk about another case study, which I would like to discuss about, is something kind of sensing the transformer oil contamination. So what we have done in this is, so in this transformer oil, so what we have kept is, we have kept a shape memory alloy. We all know when a transformer explodes, so when the transformer oil gets heated up, because of the huge amount of contamination, there will be an explosion in the transformer oil. Consider we can have an arrangement something like this. So inside this transformer oil, you are filling up with the liquid, and then you are immersing the shape memory alloy bimorph inside it. So when you are immersing a shape memory alloy bimorph inside it, because of the heating characteristics, there will be some kind of deflection which happens. And this deflection can be studied using this LDS system. And this LDS system can easily adapt the unit, and from that unit you can from this unit we can observe what is happening. Okay, so this is how we can work on the LDS unit, and we have just used it for our own application, and we have also studied in detail into this LDS. So this is an arrangement of a laser displacement sensor which is being employed, where light is being falling on the bimorph, and the bimorph is deflecting. From the deflection we can achieve what is happening. Okay, next one application what I would like to discuss about is something related to Johnson's heat engine. So here in this, if you say like this shape memory alloy, since it is a response to a waste heat, so what we can do is, like if I try to make the shape memory alloy in the form of such kind of arrangement where there is a hot and cold junction, then I can have such kind of rotation continuously. So that is like, for example, we all know we have an automobile system. You can take your simple car. When you switch on the car, in your bonnet you can expect a temperature of around easily it reaches to around 80 to 130 degrees Celsius, just on an initial idle phase. During an initial idle phase, when the temperature reaches from 80 to 130 degrees Celsius, so it is easy for us to fix that in the form of a wheel, and then you have an exhaust which is being falling on it. Because of that, there will be a rotation, and from that rotation, and a charger is coupled, and from that charger you can start harvesting the energy. So this is one very good system where the waste heat energy conversion can be employed in. Okay, so what we did is, so instead of going for a shape memory alloy wire, so we thought of making a shape memory alloy bimorph based belt. So this is a system which we developed in our laboratory, where you have a pulley kind of arrangement. So this is a roller and this is a pulley. So in this pulley, we were just placing our polyamide bimorph in it. And this is the arrangement where continuously the material powder is being fed, and from this there will be a continuous kind of evaporation. Because of this evaporation, finally you end up in some such kind of belt kind of arrangement. So from this belt kind of arrangement, so what you can do is you can just harvest the energy which is being coming out. So this is an interesting aspect with respect to this shape memory alloy bimorph. And as far as in this shape memory alloy bimorph is concerned, so this is initial setup which we developed and which we have tested in our phase, where you have a Volvo truck. Basically this is a sponsored project from Volvo, where we had an exhaust. So near to the exhaust, we made a shape memory alloy wheel, and we made the wheel to rotate, and continuously we were trying to harvest the energy coming out of it. So this is the overall results what we went. So basically we went for a different RPM. From that RPM, we were trying to study the temperature characteristics, and from the temperature characteristics, we were trying to look into the ethanol-based heat engine system. Next one important aspects which I would like to discuss over. So there are quite a good amount of videos which are available. Since there is an issue with interfacing, I am not playing the video now. At the end of the presentation, I will be playing the video so that you can get a clarity. Okay. Next one, what we are talking about is something related to developing tailor-made shape memory alloy structures. Okay, let me just give you a simple example. So we all know about this Industry 4.0. So Industry 4.0 is nothing but like you are making the machine intelligent. So when you try to make the machine intelligent, what you try to do is you try to feed a ring into it or a sensor into it, so that the system can talk to each other, as well as system can be interfaced with your internet, so that you can monitor the performance of the system through it. So that is what the idea is. So as far as in this idea is concerned, so what we are planning to do is, so we are planning to have we are planning to have the system. So in this system, if I need to integrate a smart material inside this, what should I need to do is, so I need to integrate a smart material inside it, so that whenever there is a heat is there, because of this, the smart material will sense and it will give an input. Let me just show you this example. So this is what our case study, what we have done. So basically there is a spindle is there, and there is going to be an arrangement something like this. On this spindle, you are just depositing shape memory alloy material. And on this material, you have a nozzle, and you have a mirror, and you have a laser machine. So what happens is when the laser machine, and so this is mainly meant for measuring what has happened. So when the spindle is moving at a very high speed, okay, there is going to be a vibration. So you need to arrest this vibration. At the meantime, you should also give an indication that there is going to be a failure zone. So if you try to arrest this vibration, so what you need to do is, so you need to tap it in such a way that there will be an arresting kind of thing. By arresting, you can just hold the drill bit, and with respect to that drill bit, you can arrest the vibration. So for this, I need to make the shape memory alloy in the form of a ring. So that is my major challenge. So what we have employed is, we all know about this 3D printing facility. So we went for a metal 3D printing system. So as far as in this metal 3D printing system is concerned, so what we have done is, we have used two different material, and we have fused this material exactly at the focal point of the laser, so that you can, and this is the overall system, and this is a coaxial feeder which is being kept into it. And once you try to feed the material into it through this coaxial feeder, you heat it up, and finally you can end up in such kind of structures. So the interesting part in this is, you can make a tailor-made structure coming out of it, and apart from that, you can fix this structure to get any kind of vibration arrangement or any kind of vibration analysis, etc. Second most important thing what I could observe is, you can have a cross-section geometry. From that cross-section geometry, so you can just observe how much is the variation which is coming up. So this is the overall structural analysis what we have observed. So in this structural analysis, So what I could understand is, based on this structural analysis, so we can see where exactly the nitty-gritties are happening, and there were the mechanical properties which is being placed, and we have detailedly investigated the mechanical properties of it. In fact, because of melting it, there's a chance that such kind of B2 phases are there. These B2 phases are nothing but some kind of porosities which are being embedded into it. So to prevent these porosities, we went for some kind of two different post treatment. One is some kind of laser peening, another one is some kind of laser annealing. So when we go for laser peening and laser annealing, so it is easy for us to get to make a tailor-made property of the shape memory alloy similar to the conventional system. So that is one arrangement. So these are some of the shape memory alloy bricks which has been fabricated, and in these with these shape memory alloy bricks, you can employ it in some kind of machine. But the problem in this is, since we used a laser, we had our own defects in this, which was being rectified as suggested by the some of the post processing technique, which is being mentioned over here. But finally, we could achieve some of the system almost equivalent or at par with the conventional system. Now, another, but the major drawback in this is, I would suggest that it is very difficult for us to control the required environment. So for that, we went for our own unit, where we went for some kind of I would say wire arc based additive manufacturing technique. So using this wire arc based additive manufacturing technique, you can have a control over the property of the material. And apart from that, what we did is, instead of going for a powder feeder, we went for a wire feeder, so that by feeding this wire, you can melt in and you can create any kind of structure. So that is an interesting part with this system. Okay. Next important aspect which I would like to talk about is something related to friction stir welding. As far as in this friction stir welding is concerned, so welding of shape memory alloy is a challenging task. So if I try to look into some of the applications, so this is one application where you have aerofoil structure. So in this aerofoil structure, you have a shape memory alloy which is being placed. So by just actuating this aerofoil structure, you can get a dynamic characteristics which is coming out. So that is an interesting part with this kind of system. But the major challenge in this is how to weld these structures. So in order to weld these structures, the only option which is available with me is, if I go for a conventional welding, there is a chance of there is some kind of change in transformation. When there is a change in transformation happens, so because of it loses its shape memory behavior. So as an alternative thing, what we thought is, we will go for a friction stir welding unit. So this is a friction stir welding. So we went for a friction stir welding unit, where in the case of friction stir welding, obviously you can somehow reduce the heat which is being retarded on the surface. Second thing, because of the plastic deformation, you are trying to improve. Okay. So when you try to improve the plastic deformation into it, so that what happens is, the tool and the die design will move in a particular direction, and then with respect to it, there will be a kind of retracting side which will be happening. So based on the retracting side and actuation study, so we can just say that this is the kind of arrangement which we have made, and finally this is the sample which we have welded finally, and we have just diced the sample in the form of a thin foil, or I would say in the form of a thin sample, using an EDM technique. And from this EDM, we could see a proper actuation, or I would say a proper recovery which has happened. And this is where exactly the weld region is happening. And because of this welding, you can get a straight deflection which is being coming out. So you can see that even if you weld it, you can just get a proper actuation characteristics coming out of it. So with this, we can just employ it in some kind of aerodynamic structure. And using this aerodynamic structure, you can just somehow, because of employing such kind of structures, you can somehow reduce the load on your engine, and then you can have a better efficiency. In fact, we did some simulations. Basically, we simulated the sample in such a way that by continuous loading it, you can have a continuous actuation coming out of it. Okay, so these are some of the actuation based life cycle behavior which we have employed. The next one which I would like to talk about is something related to an aerodynamic structure, basically developing an intelligent shape memory alloy based aerodynamic structure inside. So what we have done is, so we made a composite structure. So inside this composite structure, we have embedded shape memory alloy. By actuating it, you can have a deflection coming out of it. So it's a simple composite layer, but only thing is, it is something like programming this composite layer based on your requirement. So that programming of that composite layer is done using this layer which is being kept over here. So that what happens is, by whatever programming you required, you just embed the shape memory alloy inside it, and then you put the you put you integrate a composite layer into it, and that composite layer will act as an intelligent medium. So this is one good example where I could see. So here you have a layer and you have a wire which is being placed in it, and you have a composite layer which is being placed in it, and then you are trying to give some kind of strain to it. When you try to apply a strain, and because of the fiber and the resin, so you can have such kind of actuation. So this is one kind of arrangement. So how a fabrication has been done, and even I can just show you a video how we have integrated these shape memory alloys inside these composite structures, and how these composite structures are being employed for different applications. So this is a video which shows how a composite structure is being employed, and this composite structure is being deflected in such a way that you can get a life cycle behavior coming out of it. So inside this composite structure, I'm just integrating the shape memory alloy wire into it, and then you're trying to look into it. And you can get a required theta angle orientation based on the training or based on the programming which you are embedding it inside the shape memory alloy wire. So which is being kept over here. And this is the life cycle behavior which is coming up into it. Okay, and we also try, because since we want to use it for aerodynamic structure, so we were just looking into some of the applications where we can use it for a low temperature application. So for that, what we made is we made a liquid nitrogen environment. So inside this liquid nitrogen environment, we kept the shape memory alloy wire embedded composite structure, and we just made to flow the liquid nitrogen environment into it. So when you try to actuate it, you get a deflection, and from this deflection, we can see what is happening. Okay, so the next arrangement, what I would like to talk about is something kind of a Stewart platform, which is slightly moving towards a robotics behavior. So in this, these Stewart platform comes under the category of parallel manipulator. Basically, these Stewart platform has a potential application towards some kind of flight simulators or some kind of machine tool applications, etc. So we want to develop such kind of Stewart platform for some kind of optomechatronic application. So what we did is we made some kind of shape memory alloy. We trained some kind of shape memory alloy in the shape of ohm. So this ohm is being embedded into it. When you try to heat it, this ohm tries to get enlarged so that you can have a deflection which will be coming up over here. So this is what an arrangement which we used it for some kind of optical applications. And apart from that, we have also developed a small micro valve kind of arrangement. So in this micro valve, what we made is we made a shape memory alloy L kind of structure, and this is a tube which has been flowing into it. Through this tube, you can have a opening and closing of the system. When you try to open and close of the system, you can have a control over the flow rate, and from that flow rate, you can observe what is happening. So this is an arrangement what we have made, where you have a complete profile which is being kept over here. So on this profile, what we have kept is we have made an arrangement, and in this arrangement, so what we have kept is, so we have kept a micro walls, and inside these micro walls, there is, when you try to heat it, there is an opening and closing of the system which happens into the thing. And here you have a spring kind of arrangement. When you try to actuate it, an opening and closing of system happens, finally resulting in micro mixing, and from that micro mixer you can just try to get out the unit. Okay, and this is a kind of arrangement. So what we have made in this is you have a directional flow control valve. So inside this directional flow control valve, you have a conceptual design which is being placed, and you have a MS spring and you have a SMA spring. So when you try to actuate it, you can see a deflection. So by using this deflection, there will be some kind of movement which is being moving on the surface, and then by moving on the surface, you can have a fabricated prototype which is being coming up, and with this fabricated prototype, you can have an analysis which is being moving. Okay, so so now in this case, so we were more concerned about the life cycle of the shape memory alloy spring. So what we did is we made a small thermomechanical setup. So in this thermomechanical setup, what we did is we had an arrangement in such a way that you have a pulley kind of thing and you have a SMA spring kind of thing. So in this SMA and pulley kind of thing, when you are trying to actuate it, there is a deflection which is happening in it. And with respect to the deflection and the thing, you have a helium neon laser which is being placed, and you have a stationary mirror. And with this stationary mirror, there is a kind of deflection which is happening. And from this deflection, you can see what is happening into the system. So this is a setup which we made it in our lab to study the shape memory life cycle of the shape memory alloy spring. In fact, this is one characteristic which will give you a better variation where how the shape memory alloy spring works and how it moves. Okay, next is So this is with respect to the characteristics where you have a spring and you are trying to actuate it. When you try to actuate it, so you are just filling it in a hot water condition and you are trying to see how it moves. And we also want to explore the possibility of using laser based actuation, where you have a laser which is being used for heating it up so that it acts as a non-contact mode. And using this non-contact mode, you can have opening and closing of the system. And by opening and closing of the system, you can study the deflection. So what is happening? So in fact, we try to go for a non-contact actuation. So this is one small video which will give you a clarity how the non-contact based actuation happens with respect to a shape memory. So you have a shape memory strip, and you have a light, you have a laser light which is being falling on the surface, and when you try to actuate it, you can see the lifting behavior on it. So here there is no any kind of electrical circuits which is being employed into it. Second thing is, these kind of non-contact based actuations has a potential application where, for example, you have a boiler. So inside the boiler, if you have a wall where it is not possible for you to embed an electrical system into it, so in those conditions, these are an interesting aspects where you can use a laser based actuation. And these are some of the characteristics of laser based actuation, because we are more interested towards the life cycle behavior. So we are analyzing the life cycle behavior in detail, and we are working on the same. Okay, so next is this is a thermomechanical behavior of shape membrane spring which we have embedded into it. This is one case study which we have developed in our lab. So most of the people, you might have seen that they might be wearing a collar lamp. Okay, so for their cervical issue. So what we thought is, we made, since we have a shape memory alloy which is highly delicate and it has its own actuation characteristics. So we made a shape memory alloy based smart cervical collar where we have embedded a spring into it, and there are some pressure sensors, such kind of flex sensors which are being employed, and these flex sensors will have a capability to sense the pressure, and based on this actuation, it can give a certain amount of movement to the system. So this is one arrangement which we have patented. Another one is, we are also into the development of small intelligent solar tracker. So these solar trackers have a potential application where similar to your sunflower. So your sunflower will try to track the sun throughout the day. So similar to that, let us consider I have a solar panel, and I am making such kind of arrangement where a shape memory alloy spring is embedded into it, and there is a heat which is being fed into it, with a black layer into it. So what happens is, when the heat falls on the surface, because of the expansion and the contraction, there will be a kind of liberalization which happens, which tries to pull your solar panel, and so that the solar panel can track the entire day. Okay, so this is one good aspect with respect to the intelligent solar tracker. And the last one, what we are going to talk about, is something related to development of soft robotic system. Okay, so the idea behind this is, these are some of the projects which we have developed in our laboratory. So the idea behind this is, basically we want to have an underwater system. So underwater robot. So we want to mimic the complete structure of a fish in the form of an underwater system. So what we did is, we took a fish arrangement. Almost we try to replace that bone with a type of a shape memory alloy spring. So basically, we want to mimic such kind of fish kind of structure, and these are the lateral muscles and these are the bones. So we want to fabricate such kind of structures. So this is the overall block diagram. What we have, this will give you a better clarity how we have divided the different features of the fish with respect to the bellows and with respect to the structures. And this is the overall design process where you have an arrangement and you have a SMA spring which is being placed in it. And then when you try to actuate it, you can have a positive displacement coming out of it. And this is an overall control system strategy which is being employed by opening and closing and switch. So you can just have a relay switch which is being coming up. And this is the skin kind of arrangement. So in this skin kind of arrangement, so whatever is employed, so this will be employed for taking care of the buoyancy, and this is the overall control scheme. Okay, so I will just show you a small video, or I'm just switching it to the video mode now, where you can just see some of our contributions. Okay, so here you can see shape memory alloy fish which is being developed in our laboratory. So where you have a kind of arrangement, and here we have a shape memory alloy spring which is being embedded into it. and this spring would be capable enough to create the buoyancy. And here we have an onboard controller. Basically, later we have embedded this controller inside the system so that you can directly take care of it, and then it gives a forward and a return stroke coming out. So apart from this, we have also developed a small jellyfish kind of arrangement, which I would like to these are some of the systems which are developed in our laboratory. So these are some of the arrangement in our lab. So this is a 3D printing facility which we have it in. This is a metal 3D. So as in this metal 3D printing unit is concerned, so you can see that we are just feeding the wire feed. Through this wire feed, we are just so this is a wire feeder, and through this wire feeder, we are trying to fabricate shape memory structure, require tailor-made shape memory structures. Right. So I'll just show you some of the structure fabricated in our lab. So these are some of the structures which has been fabricated in our lab. So any kind of tailor-made shape memory structures can be fabricated in our lab. And this is a simple simulator unit which we have developed in our laboratory. So basically, it has a laser displacement sensor. So using this laser displacement sensor, you can study its fatigue behavior through it. So we have made an arrangement in such a way that continuously you can monitor it. Sometimes we can study the life cycle and the failure modes of the system. Okay, so this is a non-contact based laser-based activation setup which we have developed in our lab. And this is a laser forming technique which we have developed in our lab, where we could see that by just actuating it, you can create any kind of cross sections. Basically, the idea behind this is a part of die-less manufacturing. So using this die-less manufacturing, what you can do is you can just have some kind of laser treatment. So by just enlarging these laser treatment, so that you can have some kind of deflection, and with this deflection, you can just work out. Okay, so this is some kind of laser peening which we have developed. This is for industry operation. This is the composite structure which I was explaining, where an SMA is being integrated inside this structure. So these composite structures are used for some kind of missile flapper application. And this is a SMA heat engine which we have developed in our lab. So in this SMA heat engine, what you can do is you have a shape memory spokes which is being placed. When you try to heat it, you get a continuous rotation. And this is a shape memory like biomorph which we have developed in our lab. So by putting it on a hot plate, you get a straight arrangement. When I try to lift it, it comes back. So this is a jellyfish kind of arrangement which we have developed in our laboratory. So basically, it is a part of one of our projects with DRDO, where it is used for surveillance application. So the interesting part in this is here there are no heavy motors which are being placed. So what happens is whatever you can it can easily escape from radar. Second thing is it has a capability to have an onboard controller, so that you can click pictures and you can just send it to the onboard system. So it is on the development stage. And this is the robotic fish which we have developed in our lab, where we have integrated SMA springs inside it, and we have worked on it. And this is a small piezoelectric structure, self-energized piezoelectric structure, which we have developed in our lab. So basically, these piezoelectric are quite interesting. So when I try to apply load to it, I get a certain amount of what you call potential difference coming out of it. So we have made a shape, we have made a piezoelectric based mat, so that when someone stands on it, because of the power which is getting generated, you can somehow make your chemical reaction. So you can get quite a good amount of power for your chemical reaction. In fact, some kind of burglar alarm kind of arrangement also we have made. And so this is a device which is being kept over here. So if someone stands immediately, because of the load, you get alarm sound coming out. So here there is no separate electricity you need to provide. So based on the amount of the load you apply, so the alarm tries to strike. So the alarm energy is being taken care from the amount of load which is being placed into it. In fact, we are trying to implement it in a flag. So basically, where you have a flag and you have a flexible thing, so the flag can flutter at a very high speed. So because of that, since you are integrating piezoelectric structure inside these flags, you can harvest the energy through. Okay, so this is a wind tunnel experiment, and this is our piezoelectric structure. And by giving the environment, we can just harvest what is happening. The interesting part in this is, like, for example, in a remote location, the only option which is available for power generation is wind turbine blade. But nowadays, even we can use a fluttering flag to use. And this is one arrangement. It is mainly meant for this machine tool, where I have a compressor. Over this compressor, I have a piezoelectric. Because of the vibration in the compressor, I can harvest it. So like any lathe or any drilling machine, what you have, so you can just harvest such kind of unit. So these are the interesting part with respect to it. So with this, I would like to close my lecture. So any questions or any doubts, you are free to write to me. So my email ID is palaniia@iita.ac.in, and my mobile number is 9009356097. So you can write to me and you can call me anytime for any kind of collaborations. Thank you.
And thank you, sir.
Thank you, sir. So any questions?
Yes, sir. There are some questions from the audience. First question is, what are the basic function of shape memory alloy, sir?
Like a basic function of shape memory alloy, if you try to look into it, it has two behavior. One is a pseudo-elastic behavior. Another one is a shape memory alloy behavior, which is nothing but a displacement. So as far as pseudo-elastic behavior is concerned, like it can absorb the vibration. So that is what we call it a pseudo-elastic behavior. Whereas shape memory alloy behavior is concerned, with respect to the heat, it can give a displacement. Now that displacement, what you require is basically depends upon how much you are training. So these are the two aspects of shape memory.
Thank you, sir. Next question. Challenges faced in fabrication of shape memory alloy, sir.
Okay, see, as far as fabrication of shape memory alloy is concerned, I take it in three different ways. One is thin film, another one is bulk, and third is some kind of machining characteristics like welding, some kind of forming, etc. In all these three cases, there are challenges which are available, because the reason is this shape memory alloy is temperature sensitive. Even a mild variation in the temperature will somehow affect your performance capability or your functionality. So whatever we are going to employ, we should have a strict control over the temperature capability. Like for our thin film also, we normally used to deposit at a substrate temperature condition. So in this substrate condition, we need to have some kind of window, and within that window only we need to work. That is one thing. Second thing which I would like to talk about is like second thing which I would like to talk about is with respect to bulk. So with respect to bulk is concerned, we have seen this 3D additive manufacturing. In additive manufacturing, what happens is you are using powders. So because of that, again, a temperature control comes into the picture. When you try to fuse the powder, there is a chance that it may lose its shape memory property. So that is why we have developed our own wire arc based additive. So where we are getting a better control. And the fourth, if I would like to see, fabrication including forming and welding is challenge. That is why we went for a friction stir welding, as well as formability of shape memory alloy. We prefer laser form, where we could achieve a better result.
Thank you, sir. The next question. Should we consider tribological properties also for shape memory alloys for different applications?
Yes, we should also consider the tribology property of shape memory alloy if the shape memory alloy is in touch with some kind of dynamic structure. Like for example, I have shown shape memory alloy which is lifting here and up and down. So for example, if I need to keep a load over here, obviously there is going to be a tribological effect. Okay, so that we need to take care of. But basically, since if you are taking nickel titanium based shape memory alloys, you can get a better tribology behavior. Whereas in some cases like copper base etc., you need to go for a coating, what do you call it, a mapped level coating to control the tribology.
Sir. Next question. What are the basic functions of shape memory alloy actuators in robot?
Okay. See, as far as robotic is concerned, biomimicking is one important area. Now, in fact, last 10, 15 years, people are working in that particular direction, because with the conventional motors, it is very difficult to give a particular workspace or work to reach a particular work volume similar to the biomimicking capability. Like, for example, I have a human hand. Human hand is flexible enough to do it, whereas the robot cannot do it. So in that aspect, if you try to look into it, so what we have to do is, so we can just work on it in such a way that this can work together, so that you can have a control over the biomimicking capability of it. So the shape memory alloy what you are designing should have that biomimicking behavior in it. So that is where the major challenge comes into picture. And in fact, people are exploring that option only with respect to robotics. Second one, which I'm talking about, is this soft robotics. Soft robotics is something like biomimicking similar to your human being. Okay, so or any kind of animal. So that is what we are trying to do.
Okay, sir. Thank you. Last question, sir. Using shape memory alloy, is it possible to make ornithopter?
Ornithopter, yes, it is possible. But the thing is, where you want to employ in an ornithopter, that we need to look into. In the case of ornithopter, if you want to use it for a flapping wing, then obviously this has its own application, because even we have also attempted it and it is possible. Only thing is, you need to select your frequency appropriately. So that is one a suggestion from my end.
Okay, sir. Well, thank you, sir.
Thank you very much.
Good afternoon, everyone. I am honored and lucky to have the opportunity to give you a vote of thanks on this special day. First of all, I render my sincere thanks to Lord Jesus Christ. I hope you all enjoyed this session. I liked Dr. A. Palani sir's speech. The way in which he explained this subject was extraordinary. We are very thankful to our management, respected GM Development Dr. Jayakumar, and our respected Principal Dr. Velmurugan. My sincere thanks to Head of the Department Dr. Joe Patrick, Mr. Arthur Jabaraj, Mr. Javanesar Sadishpal, Dr. Nidhimanikam sir, and all my colleagues and student volunteers for their support. This webinar was made successfully only because of the well-wishers, followers, and the participants of this event. On behalf of our institution and management, I sincerely extend our heartfelt thanks to all for making this event success. With these warm words and a kind message, we move to the end of today's webinar. Thank you.